Picture this. March 8, 1970. Lyons Drag Strip, California. The air smells like nitromethane and burnt rubber. Don Garlits, the most decorated drag racer alive, straps himself into Swamp Rat 13. 2,000 horsepower of supercharged Chrysler Hemi sits 6 inches from his feet. 20 years of racing, 32 championship cars, a world speed record of 243 miles per hour. He's done it all. He's seen it all. He hits the throttle. The 2-speed transmission detonates. Not fails, detonates. The clutch pack, spinning at 8,000 RPM, turns into shrapnel traveling at bullet velocity. It tears through the firewall like paper, through the floorboard, through the driving shoe on Don Garlits' right foot. The car splits in half at 180 miles per hour, and when the safety crew reaches the wreckage, half of Garlits' right foot is gone, severed at the arch. Here's the thing. Every serious racing journalist in America assumed they were writing his obituary that afternoon. Not a retirement story, an obituary. Because that's what drag racing did to men in 1970. It ended them. This is legacy motoring. And I spent way too much time thinking about engineering revolutions that came from catastrophic failure. If you're someone who wants to understand how the most dangerous sport in America became exponentially safer, and how one man's worst day became motorsport's greatest turning point, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. What happened next is the part they don't teach you. While Garlits lay in Pomona Valley Hospital with blood soaking through his bandages, while his wife Pat begged him to walk away and every rational person in his life agreed with her, Don Garlits was not processing grief. He was not counting his blessings. He was not making peace with retirement. He was drawing the future of drag racing on a notepad. Let me put this in context for you, because the numbers are brutal. Between 1965 and 1970, drag racing killed or permanently maimed dozens of top fuel drivers. 7 fatalities in top fuel alone in 1969. Transmission explosions were the single biggest killer. When a clutch pack let go at speed, the cast iron bell housing, which was supposed to contain it, performed about as well as a cardboard box. Drivers lost feet, lost hands, lost their lives. Insurance companies were abandoning the sport entirely. Tracks were closing. And here's what most people don't realize. Every single team in Top Fuel knew the problem. They understood the physics, they understood the danger, and they kept building the same car because it won. To understand why Garlits changed everything, you have to understand what everyone was building in 1970. Every Top Fuel dragster ran one configuration. Massive supercharged engine mounted in front of the driver, 2-speed transmission directly behind it, differential connected by a short drive shaft. The driver sat directly behind all of it, separated from 2,000 horsepower by a thin firewall that had already proven it could not stop shrapnel. The front engine configuration had dominated since drag racing began in the 1950s. The logic was sound. Engine weight over the front wheels helped with traction. The long nose gave stability at speed. Chrysler Hemi engines were making 1,800 to 2,000 horsepower on nitromethane. Quarter-mile times had dropped under 6 seconds. Speeds exceeded 240 miles per hour. The formula worked. Nobody serious questioned it. Look, rear-engine dragsters have been tried before. Mickey Thompson built one in 1954. It handled terribly, and he abandoned the concept. Tony Nancy tried again in 1964. Couldn't get traction. The Dodge Colt Funny Car team experimented with one in 1969. It was slower than every front-engine car in the field. The verdict of the entire sport was clear and unanimous. Rear-engine dragsters were a dead end. Don Garlits was aware of all of this. He'd been racing against those failures his entire career, and lying in that hospital bed, missing half his foot, facing the near certainty that he'd never race again, he became convinced that the entire sport had it completely backward. Not slightly wrong, not in need of minor adjustment, fundamentally, categorically, dangerously backward. Now, you might be thinking, what does a man who just lost half his foot know about engineering that 20 years of professional racers missed? And that's exactly the right question, because the answer is that he didn't know something new. He saw something old in a completely new way. The front engine car put all the danger between the driver and the finish line. Every component that could kill you was pointed directly at you. Garlits' insight was almost childishly simple. What if you put the driver in front of the danger instead of behind it? By December 1970, 9 months after the accident, Garlits was in his shop in Seffner, Florida, building Swamp Rat 14. Not watching, not supervising, building, with a modified foot, and a conviction that the entire racing world was about to discover it had been wrong for 20 years. The engineering decisions Garlits made on Swamp Rat 14 were not incremental. He didn't move the engine back a few inches. He didn't tweak the chassis geometry. He scrapped every assumption the sport had ever made and rebuilt from physics. Start with the chassis. Front-engine dragsters were compromised by their own architecture. Frame rails had to narrow at the front to route around the engine block, then widen toward the rear. This created stress concentration points and unpredictable flex characteristics. Every team dealt with it because every team ran the same layout. Garlits' rear engine design could run parallel straight frame rails from front axle to rear, uniform cross-section, predictable behavior, easier to tune. The chassis itself was 220 inches long, actually longer than most front-engine cars. This directly addressed the stability criticism that had killed every previous rear engine attempt. Here's where it gets really interesting. Garlits placed the driver's cockpit forward directly between the front wheels. This was the move everyone else had missed. It wasn't just about getting the driver away from the engine. It was about where the driver's mass needed to be for steering control. Previous rear engine experiments had kept the cockpit in roughly the same position relative to the car, which put the driver too far back, making the steering dangerously light and twitchy. Moving the cockpit forward fundamentally changed the steering geometry in exactly the right direction. The engine, a 426 cubic inch Chrysler Hemi making 2,000 horsepower, went behind the driver, directly over the rear axle. This placement is the engineering heart of the entire design. Front-engine cars depended on violent weight transfer during launch. The car's nose would lift, shifting mass rearward onto the drive wheels to create traction. It worked, but it was violent, inconsistent, and time-consuming. In Garlits' design, the weight was already there. The engine, supercharger, and associated components totaled over 900 pounds, sitting directly over the drive tires. No transfer required. Instant, consistent, massive traction from the moment the clutch engaged. Let me give you the specific numbers because they matter. The supercharged Hemi weighed 680 pounds. The torque transmission added 145. The differential was 95. 920 pounds of mass over the rear axle before you add fuel, body panels, or the rear wing. Compare that to a front-engine car where maybe 300 pounds of that total sits over the drive wheels at launch, and even that only transfers rearward if everything goes perfectly. The aerodynamics were equally revolutionary. And here's something most people don't realize about front-engine dragsters. They generated serious lift. That long nose acted like an aircraft wing. At 200 miles per hour, a typical front-engine car generated roughly 800 pounds of aerodynamic lift, pushing the entire car upward. At 240 miles per hour, that number exceeded 1,200 pounds. Drivers described maximum speed as driving on ice, the car lighter, less stable, harder to control, precisely when you needed it most controllable. The aerodynamics were equally revolutionary. And here's something most people don't realize about front-engine dragsters. They generated serious lift. That long nose acted like an aircraft wing. At 200 miles per hour, a typical front-engine car generated roughly 800 pounds of aerodynamic lift, pushing the entire car upward. At 240 miles per hour, that number exceeded 1,200 pounds. Drivers described maximum speed as driving on ice, the car lighter, less stable, harder to control, precisely when you needed it most controllable. Garlits' short-nose design generated maybe 100 pounds of lift at 240 miles per hour. His rear wing generated 400 pounds of downforce directly over the drive wheels. Net effect, 300 pounds pushing the car into the track at maximum speed. The car got more stable as it went faster, not less. This is the aerodynamic property that separates genuinely fast from dangerously fast. And Garlits achieved it not by studying aerospace engineering textbooks, but by thinking clearly about what his design was actually doing to the air around it. The clutch system required complete reinvention. In a front-engine car, the clutch connected engine to transmission through a conventional bell housing arrangement. The violence of that connection, and its tendency to become a grenade, was the reason half of Garlits' right foot was in a medical waste bin in Pomona. His rear engine design used a direct drive system, 3 discs, 18 inches in diameter, made from sintered iron, compressed by 3,600 pounds of spring pressure. No conventional bell housing, no drive shaft. The engine's crankshaft connected directly to the differential input. Every horsepower went straight to the wheels with minimal mechanical loss. Here's a detail that doesn't get enough attention: the groove pattern on those clutch discs. Conventional front-engine clutches used radial grooves for oil evacuation. Garlits discovered through testing that radial grooves created harmonic vibrations at certain RPM ranges, subtle resonances that cost power and accelerated wear. He developed a spiral groove pattern that evacuated oil efficiently while canceling those harmonics. The clutch could handle 20% more power without any increase in size or weight. Every top fuel car running today uses a variant of that spiral groove design, and virtually nobody in the sport knows where it came from. Now, you might be thinking about safety, and you should be, because Garlits certainly was. The driver in a rear-engine car sits ahead of every component that can kill him. Transmission explodes, debris travels backward. Engine fire, flames move away from the cockpit. Fuel line ruptures, the airflow carries it rearward. Garlits added a 1/4-inch steel ballistic shield between the cockpit and engine, thick enough to stop shrapnel, and moved the fuel tank forward to a protected position between the driver and the front axle. In a head-on impact, the driver's legs would contact the chassis structure, not an engine block. The safety improvement wasn't theoretical. In 1969, Top Fuel had 7 fatalities. In 1970, 6 deaths. These weren't incidents caused by recklessness or bad luck. They were caused by drivers sitting directly behind components designed to operate at the absolute edge of material science, with no meaningful protection when those components failed. Garlits had experienced this personally. He built the solution personally. By January 1971, testing began at Garlits' home track. The first runs were disasters. The car couldn't be driven in a straight line. Look, this is the part of the story that usually gets glossed over. The part where the revolutionary idea fails completely, and the inventor has to figure out why. The steering problem was fundamental. In a front-engine car, the driver sits far behind the front wheels, and the steering geometry is tuned for that distance. The ratio between steering wheel input and wheel angle is relatively aggressive because the driver needs to be able to respond quickly at speed, and the long distance from his hands to the front axle dampens the physical feedback. Move that driver forward, put him right between the front wheels, as Garlits had done, and that same steering ratio becomes wildly sensitive. Tiny inputs at the wheel created dramatic direction changes. Garlits couldn't keep the car in his lane at full speed. He went back to the shop. Longer steering arms, completely different geometry, more caster in the front suspension to add self-centering force, a larger diameter steering wheel to give finer physical control over the inputs. The changes took 6 weeks to engineer and implement. Problem 2. The clutch engagement was wrong. In a front-engine car, you want aggressive initial clutch bite. That violence is part of the traction mechanism. It shocks the chassis into weight transfer. In Garlits' car, all that weight was already over the rear wheels. An aggressive clutch just broke the tires loose.
He needed progressive engagement, soft initial contact, gradually increasing clamping force as the car accelerated and the tires could handle more torque. The engineering required custom ground friction surfaces with precisely controlled coefficient variations across the disc face. No supplier made this. Garlits designed it himself. Problem 3. Front-end stability at speed. This one is counterintuitive. You'd think that with most of the weight over the rear axle, the front end would be too light and tend to rise. And it did, but not for the reason most people assume. The real issue was the aerodynamic balance. At speed, the small amount of lift generated at the short nose was disproportionate to the front axle load. Garlits solved it with ballast, 70 pounds of lead, mounted as low as possible in the nose structure. Final weight distribution, 82% rear, 18% front. The calculation was precise. Any more rear bias and the car would stand on its back wheels at launch. Any less and he'd sacrifice his traction advantage. By March of 1971, exactly 1 year after the accident, Garlits loaded Swamp Rat 14 onto the trailer and headed to the Gator Nationals in Gainesville, Florida.
The reaction from the field was what you'd expect from a sport that had been doing things one way for 20 years. Don the Snake Prudhomme said it looked like Garlits had built his car backward. Tom Mongoose McEwen joked that Big Daddy had finally lost it, along with half his foot. Track announcers described it as an experimental curiosity. Several crews didn't bother walking over to look at it. First qualifying run, 6.77 seconds at 218 miles per hour. Not a record, but the car went arrow straight. No wheel stand, no handling drama, no deviation from the groove. For a first competitive run, that was significant. Second qualifying run, 6.61 at 223. Now people were paying attention. In eliminations, Garlits made it to the semi-finals before losing to Steve Carbone's front-engine car. He hadn't won, but he demonstrated something that nobody could dismiss. The rear engine configuration was competitive right out of the box on its first outing, with a driver who was still learning how to operate it with a reconstructed foot. Here's what the other teams noticed that the announcer didn't mention. In a front-engine car, that massive supercharged Hemi engine sits directly in front of the driver's face. You literally cannot see the Christmas tree starting lights without leaning sideways. You can't clearly see the central line of the track. At 240 miles per hour, you're navigating primarily by peripheral vision and memory of where the walls are. Garlits, sitting ahead of his engine, had a completely unobstructed view. Perfect sight lines to the tree, to the track surface, to the finish line. In a sport measured in hundredths of seconds, the ability to react to the starting lights without a half-second compensation for your own obscured vision is an enormous advantage. The psychological dimension was equally significant. In a front-engine car, every run began with the knowledge that you were sitting behind a machine that had killed your colleagues. That awareness lives in a driver's body, whether they acknowledge it consciously or not. It affects reaction times, throttle application, willingness to push when conditions are marginal. Garlits, with the danger now behind him, felt it immediately. He described post-race interviews from 1971 as racing for the first time without a constant background awareness that the next explosion could be his last. June 19, 1971, Lakeland International Dragway. Garlits ran 6.10 seconds at 231.88 miles per hour, a new track record. Not just competitive, fastest in the country on that day. The rear-engine Dragster wasn't an interesting experiment anymore. It was the quickest car in America. The response from the establishment was immediate and fascinating. Other teams began building rear-engine cars, and they began failing badly. Jim Booker built one and crashed it. Roy Tyner built one that couldn't hook up at launch. Chris Karamesines built one that handled like a shopping cart at speed. The failures were real, and the traditionalists pointed to them as evidence that Garlits had gotten lucky, that his results weren't repeatable, that the configuration was inherently flawed.
Here's what most people don't realize. They were copying the layout and ignoring the engineering. Moving the engine behind the driver is trivially easy. Getting the weight distribution to 82/18 at the correct center of gravity height, developing a progressive clutch engagement curve matched to that weight distribution, tuning the steering geometry for a forward cockpit position, developing tire compounds specifically for a car with static rather than dynamic rear loading, these details took Garlits 18 months. The teams trying to shortcut that process were building the shape of the innovation without the substance of it. The distinction mattered enormously, and it explains why the rear engine revolution happened over a period of about 2 years rather than overnight. September 1971, Indianapolis Raceway Park, the U.S. Nationals, the biggest event in drag racing, equivalent in prestige to the Indianapolis 500 for open-wheel cars. 600 teams entered, the nation's best top-field drivers on the most demanding track in the country. Don Garlits won it in Swamp Rat 14 with a 6.21 at 234.98 miles per hour. This wasn't a regional track record or a field that happened to be weak on a particular afternoon. This was the U.S. Nationals, and Garlits beat every front-engine car in the country to win it. The rear-engine Dragster wasn't competitive anymore. It was dominant. The establishment's response moved through predictable stages. First, denial. The track win was a fluke, conditions were unusual, Garlits' experience level was exceptional and couldn't be replicated. Second, restriction. Several tracks petitioned the NHRA to require rear-engine cars to run in a separate class, arguing they were unfair competition. A few claimed safety concerns, which was almost surreal given that front-engine cars had been responsible for dozens of deaths and rear-engine cars had yet to produce a single fatality attributable to the configuration itself. Third, capitulation. By December 1971, Don Prudhomme, the Snake, the man who'd publicly mocked Garlits' car at the Gator Nationals, was building a rear-engine dragster. Prudhomme was not sentimental about equipment. He drove whatever was fastest, period. When he switched, it sent a signal to every other competitive team in the country.
Tom McEwen switched. Connie Kalita ordered one. Within 6 months of the Nationals' win, roughly half the serious Top Fuel field was either racing a rear-engine car or actively building one. By 1973, you could not realistically compete in Top Fuel with a front-engine car. The last front-engine Top Fuel victory at a national event was Rich Soesby at the 1972 Winter Nationals. After that, it was over. A configuration that had been universal for 20 years was obsolete within 30 months. Here's what most people don't realize about how fast that is. Motorsport is intensely conservative. Teams develop expertise in specific configurations. Mechanics build careers around specific architectures. Sponsors invest in specific images. Changing configurations means scrapping existing equipment, rebuilding institutional knowledge from scratch, risking competitive results during the learning curve. The barrier to change is enormous. For an entire sport to abandon its universal configuration in under 3 years represents a pace of adoption that's nearly unprecedented in racing history. The safety data drove it as much as the performance data. In 1972, the first full year with significant rear-engine participation, drag racing deaths dropped from 6 to 2. By 1975, for the first time in the history of Top Fuel competition, the sport recorded 0 driver fatalities. 0. In a sport that had been killing people every season for 2 decades. Let me put that in more concrete terms. Between 1965 and 1970, roughly 35 Top Fuel drivers suffered serious injuries or death, most from transmission and clutch failures. Between 1975 and 1985, after the rear-engine transition was complete, the number of deaths attributable to drivetrain failures was effectively 0. The engineering change didn't make crashes survivable. Cars still hit walls, still caught fire, still went airborne, but it removed the most reliable mechanism of driver death. The components most likely to catastrophically fail were now pointed away from the driver rather than at him.
Insurance companies returned. Prize money increased substantially. Television coverage expanded. ABC's Wide World of Sports added drag racing to its rotation, and the sport found a mainstream audience for the first time. Sponsorship from major corporations became possible. All of this economic transformation traces back to the viability argument. A sport that kills its participants on a regular schedule cannot sustain commercial relationships. Garlits made drag racing survivable, and survivability made it commercially viable. The international adoption was rapid. Australian drag racing converted almost simultaneously with American Top Fuel. European teams that had struggled to develop competitive front-engine cars found the rear-engine design easier to build correctly. The simpler chassis geometry and accessible drivetrain made the learning curve manageable. Japanese engineers studied the design in detail and applied its principles to their own motorsport applications.
Here's a detail about this period that I find genuinely remarkable. Don Garlits never patented the rear-engine dragster design. When a reporter asked him why in 1973, he said he wanted everyone to copy it. He wanted the design to spread as fast as possible because he'd watched friends die in front-engine cars for 20 years and wanted that to stop. By choosing not to patent, he probably gave up millions of dollars in licensing fees. He made that choice consciously and without apparent regret. Consider the counterfactual for a moment. If Garlits had patented a design and restricted licensing, the rear-engine transition could have taken a decade longer. The teams that couldn't afford licensing fees would have continued running front-engine cars, and drivers would have continued dying in them. The decision not to patent is, in a practical sense, part of the safety innovation. It's the reason the adoption curve was 2 years instead of 10. This is where it gets really interesting from an engineering influence standpoint. The rear-engine revolution didn't stay in drag racing. The principles Garlits demonstrated, weight distribution optimization for traction, aerodynamic downforce over drive wheels, driver protection through component placement, spread through motorsport in ways that are difficult to fully trace. Formula One had been moving toward rear-engine configurations since the early 1960s, when Jack Brabham won the 1959 and 1960 championships in Cooper's rear-engine cars. But the detailed engineering of weight distribution and aerodynamic balance that Garlits worked out under competition conditions influenced how engineers in multiple disciplines thought about the relationship between mass location and vehicle behavior. Sprint car racing adopted rear-engine layouts. Funny car design borrowed directly from Garlits' aerodynamic principles. Tractor pull competitors applied his weight distribution philosophy to completely different machines. The specific solutions he developed were transferable in ways that no one fully anticipated in 1971. Let me give you the physics in more detail, because the engineering arguments are more interesting than the racing narrative in some ways. The moment arm geometry is where front-engine and rear-engine cars differ most fundamentally. In a typical 1970 front-engine top fuel car, the center of gravity sat approximately 85 inches behind the front axle. When the clutch engaged and the chassis rotated under acceleration, the moment arm, the distance over which the rotating force acted, was long enough to lift the front wheels 3 feet off the ground. Teams couldn't simply apply full throttle. They had to feather the clutch, carefully managing the rotation to keep the car from going vertical, which meant managing the power delivery in a way that inherently limited acceleration during the first critical tenth of a second. In Swamp Rat 14, the center of gravity was roughly 140 inches behind the front axle, and critically, only 28 inches ahead of the rear axle. The moment arm for lifting the front end was minimal. The front wheels might rise an inch or two, not 3 feet. Garlits could go to full throttle almost immediately. No feathering, no power management, no wasted time. The physics favored linear acceleration over chassis rotation, which is exactly what you want in a vehicle whose entire purpose is to accelerate in a straight line. The structural engineering advantages are worth understanding. Front-engine chassis design was a series of compromises forced by the layout. Frame rails had to route around the engine block, creating bends and changes in cross-section that acted as stress concentration points.
Every time the chassis flexed under acceleration, which happened on every run, those concentration points absorbed disproportionate stress. Chassis cracking was a common maintenance issue. Teams replaced frames regularly. Garlits' straight parallel rails solved this. Uniform geometry meant uniform stress distribution. The chassis flexed predictably, and that predictable flex could be tuned deliberately. You actually want some specific amount of controlled chassis flex in a drag car because it affects how the rear tires load up during launch. With a consistent geometry, you could tune that flex precisely. Front-engine chassis builders were chasing consistency in a structure that was geometrically inconsistent from front to back. The cooling dynamics were a significant practical advantage that rarely gets discussed. Front-engine cars struggled with heat management in ways that affected driver performance directly. The engine sat directly in front of the driver's face. Exhaust headers dumped heat into the cockpit. Oil temperatures regularly exceeded 300 degrees Fahrenheit. Drivers suffered radiant heat burns, dehydration, and the kind of sustained discomfort that affects concentration and reaction time over a full day of competition. In Garlits' configuration, the engine sat behind the driver in clean airflow. Natural convection carried heat rearward, away from the cockpit. Oil temperatures stayed under 250 degrees. Drivers reported dramatically better conditions. They arrived at the finish line less fatigued, more focused, more capable of consistent performance across multiple rounds of eliminations. This is a competitive advantage that doesn't show up in horsepower numbers, but absolutely shows up in championship results. The maintenance economics transformed how teams operated. In a front-engine car, accessing the transmission required removing the entire body, typically an 8-hour process that often extended into the next morning. Clutch rebuilds that took all night became standard. Between-round repairs that should have been simple became complex, time-consuming operations. Teams ran fewer qualifying passes to minimize the risk of needing repairs they didn't have time to make.
On Swamp Rat 14, the transmission was accessible from above. A complete rebuild took approximately 2 hours. Clutch changes that had consumed entire nights now took one qualified mechanic less than 2 hours. Teams could make more qualifying runs, accumulate more data, develop the car more aggressively. The maintenance advantage compounded across a full season into a meaningful competitive difference. Here's something most people don't realize about tire technology in this era. M&H's tire company, which supplied most top fuel teams, had developed their compounds around front-engine car behavior. Those tires were designed for dynamic loading. The rubber compounds and sidewall construction were optimized for a tire that starts with relatively low rear load and receives additional load through chassis rotation during launch. Garlits' car required completely different tire characteristics. The rear tires had maximum load from the moment of clutch engagement. No dynamic loading to manage, just sustained maximum load from 0 miles per hour. M&H worked with Garlits to develop compounds with softer sidewalls for initial compliance under immediate high load, and a different sensor tread compound for top-end stability. The correct tire pressure was 4.5 psi rather than the standard 5.5 psi front-engine teams ran. Small numbers, large effect. The human factor study, if anyone had been conducting one formally in 1971, would have shown dramatic differences. In a front-engine car, the driver experienced 5.5 Gs of linear acceleration, plus a significant rotational force as the chassis rotated during launch. The combined effect was disorienting. Experienced drivers described it as being simultaneously pushed back and rotated, a complex multi-axis sensation that required sustained physical effort to process and respond to correctly. Less experienced drivers sometimes experience brief cognitive disruption. All drivers experience fatigue that accumulated across a competitive day. In Garlits' car, sitting near the center of gravity, the driver experienced essentially pure linear acceleration, still 5.5 Gs, but without the rotational component. Cleaner, simpler, easier to process. Drivers reported making better decisions later in elimination rounds, the kind of decisions that separate champions from contenders.
The fire safety improvements were perhaps the most significant practical change. Front engine cars positioned the fuel tank directly behind the engine. In a fire scenario, flames swept straight back from the engine through the fuel tank area and directly into the driver's compartment. Burn injuries were extremely common in front-engine top fuel accidents. A non-trivial number of fatalities in the pre-1970 era involved drivers who survived the initial incident but died from burn injuries sustained in the subsequent fire. Garlits moved the fuel tank forward, behind the proper firewall, between the driver and the front axle. In a rupture scenario, fuel sprayed away from the engine. Airflow at speed carried flames rearward, away from the cockpit. This single change in component positioning substantially reduced burn risk without adding meaningful weight or complexity. The cumulative effect of all these engineering decisions, chassis geometry, weight distribution, aerodynamics, clutch design, cooling, maintenance access, tire development, fire safety, was not a car that was slightly better than front engine designs. It was a car that was categorically superior in every measurable dimension. And it had taken one man working in a Florida shop with a modified foot 12 months to design it from scratch after an accident that should have ended his career. Don Garlits continued racing until 1992. He won 144 major national events, 17 NHRA top fuel championships. He was the first driver to break 250 miles per hour in 1975, the first to break 270 in 1986. Swamp Rats 15 through 38 refined the configuration he'd sketched in a hospital bed, each one faster, safer, and more sophisticated than the last. He retired at 60, still competitive, still capable of winning, still innovating. He's 92 years old now and still doing interviews. He owns the Museum of Drag Racing in Ocala, Florida, where Swamp Rat 14 sits in its own dedicated space. He still has the original engineering drawings, the handwritten calculations, the test data from those early months in 1971. When young engineers visit, he apparently tells them the same thing. Don't accept that something is right just because it's always been done that way. Sometimes you have to flip everything around to see the solution. Here's what the numbers look like today, half a century after Garlits first ran Swamp Rat 14 at the Gator Nationals. Modern top fuel engines displace 500 cubic inches and make over 11,000 horsepower, more than 5 times the output of the car Garlits was driving when he lost half his foot. Acceleration from 0 to 100 miles per hour takes 0.8 seconds. The cars pull 5.7 Gs off the line and reach 335 miles per hour in 1,000 feet. The NHRA shortened the racing distance from a quarter mile to 1,000 feet in 2008. Specifically because the speeds had become too dangerous for the full distance. The cars were generating more aerodynamic downforce than the rear waist structures could reliably manage at the full quarter mile. Every single one of those cars uses Don Garlits' fundamental layout. Engine behind driver, direct drive to rear wheels, driver positioned forward between the front axle, aerodynamic package creating downforce over drive wheels. The specifics have changed beyond recognition. Carbon fiber monocoques instead of chromoly tube frames, computer-controlled clutch management instead of mechanically preset discs, 16-stage fuel injection systems instead of hill-borne injectors, wind tunnel-developed body shapes instead of hand-formed aluminum panels. The fundamentals have not changed once. The safety record of the modern era is a direct product of that fundamental layout. The driver safety cell that protected Tony Schumacher when his car went airborne at well over 300 miles per hour and survived intact. That's a direct evolution of the driver protection philosophy Garlits built into Swamp Rat 14. The ballistic shields, the fuel system isolation, the drivetrain containment, all refinements of principles Garlits established when he was working alone in a Florida shop, still learning to walk normally on a rebuilt foot. Now, you might be thinking, what does any of this have to do with anything outside of drag racing? And the honest answer is that the specific technologies are mostly contained within motorsport, but the thinking process that produced those technologies applies everywhere. Here's what most people don't realize about genuinely revolutionary engineering. It almost never comes from incremental improvement of the existing approach. It comes from questioning whether the existing approach is actually correct at a fundamental level. The teams that tried to improve front-engine top fuel cars in 1970 were working hard, spending money, applying intelligence and experience. They made real progress. But they were making a fundamentally compromised configuration marginally less compromised. Garlits stepped back far enough to see that the entire configuration was the problem. This is much harder than it sounds. The more expert you become in a field, the more deeply you've internalized its assumptions, and the harder it becomes to see those assumptions as assumptions rather than facts. Garlits had 20 years of front-engine experience when he designed Swamp Rat 14. He knew more about front-engine top fuel cars than almost anyone alive. That expertise could easily have made him less capable of questioning the front-engine layout, not more. The accident didn't give him technical knowledge he hadn't had before. It gave him a reason to actually use the critical distance from the conventional approach that expertise had been making harder to maintain. Consider the fields where this pattern has repeated itself. Surgeons who redesigned operating procedures after being told a family member's death resulted from preventable error. Engineers who questioned bridge construction methods after a collapse. Software architects who rebuilt systems from scratch rather than patching accumulating technical debt. In every case, the insight wasn't new technical knowledge, it was new willingness to question what everyone had accepted as correct. The rear engine revolution also tells us something important about the relationship between safety and performance. The conventional wisdom in 1970 was that the dangerous aspects of top fuel racing were simply the cost of the performance. You couldn't make the cars safer without making them slower. This belief was wrong, but it was genuinely held by experienced, intelligent people who had been watching the sport for decades. Garlits demonstrated that the dangerous aspects of the front-engine configuration were actually performance penalties masquerading as necessary trade-offs. The violent weight transfer that made the car dangerous was also inconsistent, wasteful, and difficult to control. The exposed drivetrain that put drivers at risk was also maintenance-intensive and hard to tune. The aerodynamic lift that made high-speed driving terrifying was also slowing the cars down. Every safety improvement in the rear engine design was also a performance improvement. There was no trade-off. The trade-off had been invented by people who couldn't see the problem from the outside. The next time you find yourself accepting a trade-off as necessary, in engineering, in business, in medicine, in any field where complex systems produce both performance and harm, it's worth asking whether you're actually looking at a fundamental constraint or whether you're looking at the accumulated assumptions of people who built the current system and never questioned its foundations. Don Garlits shows us that sometimes losing something precious, even half your foot, even your obvious path to retirement, even your place in the comfortable consensus of your field, gives you the clarity to see what everyone around you is missing. Not because loss is ennobling in some abstract sense, but because it forces you outside the frame of reference you've been operating in. It makes the assumptions visible. Every top fuel dragster on Earth, every run at every track in every country exists in the configuration it does because one man spent 12 months refusing to accept that getting maimed was simply part of the job. He drew the future on a notepad in a hospital room, built it in a Florida shop, and drove it to the starting line of the Gator Nationals with a reconstructed foot and 50 years of critics about to be proven wrong. Drop a comment below about the most counterintuitive innovation you've ever come across. What invention succeeded specifically because it did the opposite of what common sense suggested? And if you want more deep dives into the engineering decisions and engineering personalities that changed motorsport forever, subscribe because we're just getting started.